Hello, welcome to 3 Minutes Engineering Concepts. The idea of this channel is to explain any engineering concept within 3 minutes time. I will be able to explain any fundamental to advanced concept in mechanical engineering and material science. If you like the idea, then please subscribe to our channel and also share our videos and channel details to colleagues and students who can benefit from it. Thank you.
So what we have done until now, we now know what are the element-based equations after the transformation for our system, which we are trying to solve, in this case our truss system. And that looks something like this, where Ke is my global stiffness, elemental stiffness matrix, Me is the elemental mass matrix in global coordinate system, and Fe is the force vector in global coordinate system. And then we also discussed about how to transform or get these global matrices and vectors using the local coordinate, similar quantities in local coordinate systems like stiffness matrix, mass matrix, and force vector using transformation matrix. And for transformation matrix, I gave you a simple relationship here and also explain to you how you can compute those using this relationship between by finding the relationship between the local coordinate system and the global coordinate system. So in the global system of equations, once we have computed the stiffnesses, mass matrices, and force vectors for each element, let's say if we have one, 2, and 3 elements, then we have to do it for individual elements, and then we have to assemble and construct a global FE system of equations which will look similar to the elemental one, but now it has all the nodes and elemental data into it. And then we will try to find out what are the solutions. So in the last video I told you, if we are doing a static analysis, we can eliminate this part, and then we solve the system of equation where we want to find the unknown displacement. So we can take this K on the other side, take the inverse of it, and multiply it with the force vector and get the displacements at each node. Or if we are doing a dynamic analysis, and we have to solve this time differential equation. And if we are doing some free vibration analysis, then maybe we need to eliminate some other terms and find out what are the unknown frequency modes. And I gave you some examples of different types of solvers which are there in the market for that. So in my view, now we are ready to apply all these equations in the real world examples. So I will try to explain to you how you can apply those equations to any system which you are trying to solve for unknown displacements. So we are always trying to work in terms of displacements, but you can also apply the same knowledge in terms of temperatures or thermal analysis, for example, or temperature displacement analysis, which can be more complicated. So I will start with that, and I will solve a simple truss example in today's video. Okay, so example starts. It's a very simple example, and I will start with that, which doesn't require any coordinate transformation. So at least first you will know how to compute those elemental stiffnesses, mass and mass matrices, and also the force vectors, and then solve for unknown variables. And then we will move to a more complicated example where we have more than one element which requires transformation as well. So it's a uniform bar subjected to axial loading or axial force. So the bar has a length of L, as you see here, and a displacement and a force of P is applied onto it. So right now I'm not giving you any numbers, but since I want to relate this problem with the analytical solution, because it's a very simple problem and we already know the solution for that. And once we move to the real more examples, and I will give you more numerical examples into that. So consider a bar of uniform cross-sectional area. So area of the cross-section is constant throughout the length. As shown in the figure, the bar is fixed at one end, so it's fixed from this side here, and is subjected to a horizontal load of P at the free end. The dimensions of the bar are shown in the figure, and the beam is made of an isotropic material with Young's modulus of E. So when we talk about isotropic material, this means we are saying that irrespective of the direction or how you cut the sample from the material, your material response will be the same. So material orientation will not change its response. So its Young's modulus is same from whether irrespective of the direction of the pull for this material. So the first thing is, obviously I will give you the exact solution of this bar because it's a very simple problem. So we will derive the relationship for that. We always start for any structural mechanics problem, we always start with the strong form of the equilibrium equation. We already know the strong form. If you remember from previous lectures, I have repeated it many times. So the strong form of a truss member is given by this relationship here, where Fx is the surface forces, U is the displacement, x is the longitudinal direction, and E is the Young's modulus. Since the bar is free of body forces, so we can assume that Fx is 0. There is no mention of gravity or anything, so we can assume it to be 0. And this gives us a simple relationship, which is second order derivative of u with respect to x, which is a longitudinal direction coordinate system, and that should be equal to 0. So it's just this term equals to 0. You take E as a constant, it goes on the other side and becomes 0. It becomes 0. So going back to your differential equations, the general form of solution for such kind of second order partial differential equation can be easily found using this kind of integral form after the integral, and that's basically ux equals to c naught plus c1x, and it's just you are taking this integral twice, where c naught and c1s are unknown, and generally they should come or derived or determined from using boundary conditions. So in this case, our boundary condition is your at L equals to 0, your displacements are 0, and at L equals to x equals to L, your load is P. So we have two different boundary conditions. One is the displacement boundary condition, and the other one is the force boundary condition. So the displacement boundary condition for this problem can be given as u equals to 0 at x equals to 0, because we are assuming this is our x direction or x coordinate system. So this, when I substitute these values here in this equation here, then I get, or I find out that my C naught comes out to be 0. So I have found one of the constants using the boundary conditions. So based on this, now my solution for the displacement in x direction becomes like this, because my C naught is 0 based on the boundary condition. And to find the value of C1, I have different ways of doing it. So what I can do, I can use my kinematic equation, which, if you remember, is just the partial derivative of u with respect to x, and also my constitutive equation for the truss element, which is x sigma equals to E times epsilon, which is based on the Hooke's law. So these are all we have discussed many times. So what we have after substituting everything into this equation here, so this all goes here, and we find out that my stresses in x direction will be E times this epsilon x, and then I replace this epsilon x with the partial derivative of this, and I get my sigma x equals to C1 times E. So in a way, using the strong form of my equilibrium equation, I found out what is the value of the C naught, and we're using the kinematics and constitutive equation. Now I can now compute my stresses and strains if I know my displacement field. So you see, in this equation, this problem is very simple. I can solve this and find out all the unknowns which we normally find out in an FE problem. So what I know now, my stress can be related with the displacements by this relationship, using combining kinematic and the constitutive equation, and then when I substitute the value of my displacement field or derivative of displacement field, I get this kind of values. Now in order to find the value of this other unknown constant C1, I can use the other boundary condition, which is at x equals to L, my load is P. So the force boundary condition for this bar can be given as my sigma x at this point here will be such that my stress will be P over cross-sectional area A. So if I say that this is a rectangular bar which has a cross-sectional area of A, then I just divide this load with the area, and I will get the stress at this point, which is at x equals to L. And that is what this boundary condition tells you. And then I equate this equation here with this equation here, and I get the value for C1, which is P over E A. So now I know the constant, so I know everything in terms of, for example, if I want to find stresses, if I want to find strains, or if I want to find the displacements. And this is what is shown here. So my C, as you know, is given by this relationship here. I substitute this value in my sigma x relationship. So my stress in the bar will be P over A with it. So it's independent of the location. So if I'm here or here or here, it's a uniformly stressed bar, and it will have a stress value which is P over A, which is very much the reality in this simple example. While my displacement field, if I want to find displacement at any point in the bar, depending on the coordinate system X, then I use this relationship. As you remember, we derived that by integrating that equilibrium equation, and I can substitute the value of C from here into this, and I get the equation which is P over EA times X for my displacement field. So I can now also estimate if my X starts from 0 to L, how my displacement will be varying, and it seems like it's more or less a linear function depending on the X, and my final value will be P L over E A if I substitute the values of X and replace it where I am at the location of this. So now what I'm going to do, I'm going to repeat the same exercise and try to show you how you can use those FEM based equations which I gave you in the previous videos, and I have been repeating them many times, how I can use those to find out the same things using FEM equations. So the only difference in these cases is I need to first start with my stiffness matrices. So my elemental stiffness matrix, as you remember, was B times the E matrix times B times the volume. And I give you the relationship based on my shape functions, which was this. So, and if you remember my elements, I only just choose that my bar has one element and it has two nodes, node 1 and node 2, which can have displacements of u1 and u2. And based on that, my element stiffness matrix from my previous video can be calculated using this simple relationship using linear shape functions. In this case, there is no need to perform coordinate transformation, as the local and global coordinates are the same, because we are assuming that my small x and the global coordinate system are the same, because we only have one element, so there is no point of doing that. But in the later example, when we will have different members with different orientations, it will require that transformation, and I will show you how you can do that. Also, there is no need to perform any assembly, because we are assuming there is only one element, so element numbers are equal to 1 in this case. So we are free to that. So just to give you an idea about only local elemental stiffness matrix computation, how to do that, and also how to compute the mass matrix in local coordinate system for each element, and also the force vector. So now what I do, once I compute the stiffness matrix, I don't need any mass matrix because it's a static problem, so I don't need the term. So you remember my equation was K times D equals to F, right? So in this case, again, there is no global or elemental. They are the same because we have only one element, and also we don't have any coordinate transformation. So I'm using this equation here. So you remember my K is given by this. If I look at my D matrix, I have only two nodes here. So I have only 2 degrees of freedom, or 2 displacements, U1 and U2. And also my force vector will be my force at node 1, which is unknown. We don't know what is the force here, while based on the boundary condition, we know the force which is equal to P at x equals to L, and that is given by this at U2. So we know these quantities, so we know my force vector, my displacement vector, and my stiffness matrix in this case. So in order to find out, so we don't know this, but we know this, but we don't know this. But in order to solve this, because what I told you was I will take this stiffness matrix on the other side here, and I will take the inverse and I solve it, but I still don't know this value here. So instead of having this force, we have a displacement boundary condition on this side, and we are given that u1 equals to 0 at this node u1, and that's what we're going to use to eliminate some of the equations or some of the variables from this matrix form, and solve for the unknown displacements, which will be in this case u2. So the best approach in this case is by elimination. What you do is you try to eliminate the things which are known to you, and for example, if you have fixed boundary condition, this means my u1 here, my u1 is 0. So if I replace this u1 with 0, then I can just eliminate this equation, this row and this column from these matrices. So I have reduced my system now, and I can now say that my equation would be AEL times U2, right, equals to F2, which is P, and that's what I do here. So my AEL, when it goes on the other side from here to this side, I will have my U2 equals to P and then L over AE, which comes from the other side. So this way I can find out my displacement at node 2. And you remember this was the same value we got from the exact solution or analytical solution. If we don't put this L here and we say that we want to find throughout the element, then again we can vary L and we can find out at each point in the finite element what is the value of U2. Once we know the displacements, we can compute the other quantities. So based on those equations, we now know that my displacement is 0 at x equals to 0, or at node 1 equals to 0, and at U2 my displacement is around this, which is at x equals to L. And what I do, I just substitute these values into my displacement equation, which was based on the shape functions and the displacements at the nodes. Since I know the displacements at the nodes, so I can substitute them here. I also already know my shape function, so I can find out inside the element how does the displacement really vary in the context of finite element solution. So that's what I do here. You remember my shape functions are given by this term here, this vector here, and my displacements are only two nodes, so two displacement values. I replace the U1 and U2 with the values, as you remember we computed just in couple of slides back. And when I solve this displacement equation, which means this term times this plus this term times this, so I will ultimately this term times this becomes 0, so I will only have P over EA times L, obviously, and then I have X over L here, so L cancels out and I have P over EA times X. And if you remember, this was the exact solution as well. So my FE solution and my exact solution are leading to the same result in this case, and now I know what is the displacement at each spot in this case, and it can also show there is a linear dependence on X, and I also know what is the maximum one. I can also compute the stresses based on my constitutive equations and also the strains using the kinematic equations. So that's what I do here. I use my constitutive equation. If you remember, I gave you this explicit relationship here, E times B times DE, and my B is always the Laplace operator or differential operator times the shape function vector, and this is given by this, and my B is always this in the case of truss elements in the linear when I use a linear shape function. So I do that. I am not using any transformation, so this goes away in this case. So my sigma x will be, or stresses in x direction will be E times B times DE. My E remains the same. My B is based on this computation here, and my displacement DE, as you remember, were U1 and U2, while U1 is 0 because it's fixed here at this point, and U2 is, we already have computed that. So based on these values, once I substitute everything and simplify, I get the stress value, which is P over A. So this is again the same as what we found using the exact solution, and which is very much the same as using the simple so basic solid mechanics as well, that stress will be load force over the area for any bar which is loaded in the axial direction. So I hope things have started to make some sense now. I gave you the relationships directly, so you can use those for any structure. So this is only 1D or 2D structure right now, but you can apply it to complicated 2D structure or complicated 3D structure as well, using the similar relationships, because these are all in matrix form. So if you are working with 2D, then the matrix order will become 2 by 2 or 3 by 3 depending on how many dimensions, nodes, etc. you will have in your case. So I hope things are making more sense now, and in the next video I will try to solve another problem with multiple truss elements, and which will require, for example, coordinate transformation, and also will require assembly because we will have more elements at different orientation in the truss structure. And yeah, until that time, stay safe. It's difficult times for every one of us, and that's why it's taking more time for me to make more videos, but I will keep on going as the time allows me. So hopefully you will like this video. So if you like this video, please like or subscribe to our channel as well as our Facebook page. And if you want any other concept other than FEM or some other things in solid mechanics or material science, then get back to us or get back to me, and I will try to prepare a short video on that as well, so that you can make so that it makes more sense to you guys. Thank you very much again, and stay safe.